Stellar mass is a fundamental parameter in astrophysics that governs the life cycle, evolution, and ultimate fate of stars. Accurate measurements of stellar mass provide critical insights into a wide range of astronomical phenomena, from star formation to galaxy evolution. In this description, we will explore the various observational techniques used to measure stellar mass, highlighting their methodologies, applications, and limitations. Mass is a cornerstone property of stars, dictating their luminosity, temperature, and lifespan. Despite its significance, stellar mass is not a directly observable quantity. Instead, astronomers rely on indirect methods that combine theoretical models with observations of stellar and binary systems. This essay will delve into the most common techniques, including binary systems, stellar dynamics, astroseismology, gravitational microlensing, and stellar population synthesis. Binary systems, where two stars orbit a common center of mass, provide the most direct and reliable method for determining stellar mass. These systems are classified into visual binaries, spectroscopic binaries, eclipsing binaries, and astrometric binaries, each offering unique observational opportunities. Visual binaries are systems where both stars can be resolved spatially through a telescope. By tracking their orbital motion over time, astronomers can determine the orbital parameters, including the semi-major axis and orbital period. Spectroscopic binaries are systems where the star's spectral lines exhibit periodic Doppler shifts due to their orbital motion. These shifts allow the measurement of radial velocities, which, combined with orbital inclination, yield the mass function. By combining radial velocity curves with additional information, such as eclipses or astrometric data, the individual stellar masses can be derived. Eclipsing binaries are systems where the orbital plane is aligned such that one star periodically passes in front of the other, causing a measurable dip in brightness. These systems provide critical information about the radii and masses of the stars when combined with spectroscopic data. The precision of mass measurements in eclipsing binaries is unmatched, often reaching accuracies of a few percent. In astrometric binaries, only one star is directly visible, while the other induces measurable wobbles in the visible star's position. These systems require long-term monitoring with high-precision astrometry, such as that provided by the Gaia mission, to infer the mass of the unseen companion. Star clusters, particularly globular clusters, provide natural laboratories for studying stellar mass. The motions of stars within a cluster are influenced by the cluster's total mass, which can be inferred using the virial theorem. Astroseismology, the study of stellar oscillations, has revolutionized our understanding of stellar interiors and masses. Oscillations manifest as periodic variations in a star's brightness or radial velocity, which are sensitive to its internal structure. The two key observables in astroseismology are the large frequency separation and the frequency of maximum power. Space-based missions like Kepler and TESS have provided high-precision data, enabling mass estimates with an accuracy of 5 to 10%. Gravitational microlensing occurs when a massive object passes in front of a background star, bending its light and causing a temporary brightening. The shape and duration of the microlensing event depend on the mass of the lensing object. Microlensing is particularly useful for measuring the masses of isolated stars, stellar remnants, and exoplanets, as it does not require light from the lensing object. In distant galaxies, individual stars cannot be resolved, necessitating indirect methods to estimate stellar mass. Stellar population synthesis combines theoretical models of stellar evolution with observed spectra or photometry to infer the mass distribution of stars within a galaxy. This technique relies heavily on assumptions about the initial mass function, star formation history, and metallicity, introducing significant uncertainties. Each technique for measuring stellar mass has its limitations. Binary systems require favorable orientations and long-term monitoring. Astroseismology depends on precise data and well-calibrated models. Gravitational microlensing is rare and often provides limited information about the lensing object. Stellar population synthesis is model-dependent and prone to degeneracies. Overcoming these challenges requires advances in instrumentation, data analysis, and theoretical modeling. The future of stellar mass measurements is bright, thanks to upcoming missions and technological advancements. The James Webb Space Telescope and the Extremely Large Telescope will enable unprecedented studies of stellar populations and binaries. Continued data from Gaia will refine astrometric measurements, while next-generation asteroseismology missions will provide insights into stellar interiors. Additionally, gravitational wave observatories like LIGO and Virgo offer a novel avenue for probing the masses of compact objects. Measuring stellar mass is a cornerstone of astrophysical research, underpinning our understanding of stars, galaxies, and the universe at large. The diverse array of observational techniques, from binary systems to gravitational microlensing, demonstrates the ingenuity and adaptability of astronomers in tackling this fundamental challenge. As technology and theory continue to advance, so too will our ability to measure stellar masses with greater precision and accuracy, unlocking new frontiers in astrophysics.